And I realized I've never gone over the gambit of quantum mechanics, the model problems. Like we started with free wave, then we had particle in a box. There's like a little litany in 3 dimensions, and I never really went over them. So I'm going to do that, and then that'll segue back into 3D rigid rotor, which is where we're still at. And then we're done with that, and then we're on hydrogen atom, which, it's not, given that I'm not going to actually solve the differential equation. That's what when I was your age, and we did hydrogen atom, we spent an entire week doing the different diffie-q to solve it. We had to take diffie-q. So the instructor said, okay, we're going to spend all week, so 3 days, all week, doing the diffie-q on the hydrogen atom. And I really don't want to do that. It's just no, so I'm not. Anyway, so that will make it a bit easier. And just like a lot of things, it's just 10 miles long. That's the problem. Okay, so anyway, I think this will help keep straight what's what. It reinforces a lot of the lessons that we apply towards 3D rigid rotor in hydrogen atom. If we start with not particle in a box, so I know that I spend way too time reviewing on every class, but let's start with 2D particle in a box, and 3D is of course trivially related because all you do is, well, let me just write nx pi x over L. And you can see K. By the way, I don't recall if this was like the last question on the exam. K's are basically always 1 over L. That is the answer to the last question, by the way. K is 1 over L. You can also say 1/3 L. Just heads up, there were 2 answers. But notice the K's are always something. It's either 1 over L or pi over L. It's always something over L. Now there's some deeper reasons for that, but maybe come by office hours if you want to know them. I don't want to blow too much time on that. So anyway, so here's the 2D case, and then and I figured this out as usual just because I know that signs are okay for flat potential. I know I have to build in excited states. I have to build in nodes, and then I can apply the Schrödinger equation, and I get this. I get the potential for degeneracies, which is kind of neat, but I don't really think we need to harp on that. Of course, I'm writing out mass. I have to write that out now because m is a quantum number. And there's no 2 pi's present because the h bar ate that by turning into an h. Anyway, so I mentioned to you that I remember saying initially, like, okay, when we go from 1D free wave, when we go to higher dimensions, it's really easy, and I don't want to spend a lot of time on it because that's why. If we're doing 3D, then add a z, right? It's really simple. What's not simple is when we go to 2 dimension. When we start making this circular, we start using cylindrical coordinates and then rotational. So we next went to 2D rigid rotor. There we go. So that's the radius. The wave function. Now this is actually a subset. This is a limiting form of another thing, and I'm going to show you that. I'm just reminding you of the order that we went to class, but I'm going to kind of do this in a different way in a second here. Anyway, so there's our wave function. The energies are the square of the z angular momentum. There's only z angular momentum because it's confined to be in the yz plane. Remember, that's unrealistic. Things are 3-dimensional, right? And because it's only because we fixed the radius. And by the way, here's an answer to one of the exam questions. The energy drops for a 2D rotor because the radius hides inside of I. That was actually for sure. Maybe you got it, maybe you didn't. If you didn't get it, again, it's not too many points. Then we see quantization because there's only certain integer values of angular momentum. And that, of course, means that the angular momentum is in discrete. H bar, 0, 1, -1, yada, yada, yada. Okay, now this is what we covered, but now let me back up a little bit and show you where this comes from. And you did see some of this. So I'm gonna put this in a different context. I'm gonna do a particle. So here's our circular trap, but here's our circular track. But let me point out what I'm going to do instead is I'm going to have, let's call it an electron. It's a particle in a circle. So it's just like this. It's entirely like this, except I made the floor circular, right? So it's like really quite trivial. I'm not going to call this R. I'm going to call this radius. So anyway, that's obvious. I'm not going to call it R anymore because you want R. R is now R is R. But I'm not going to fix it. So not hard, right? So it's like a particle, and it's just like this. So remember that it's a particle and it's just moving around, right? Like this. Don't get confused with the fact that I drew it all 3D-ish. This particle, it's the same deal. It's just got circular symmetry. It just wanders around like that. Okay. Now, so where does this come from? This is a particle in a circle, in an infinite circle, when the radius is fixed. So in this case, I'm not fixing the radius, so what do you have? -8. So this is where I messed up part of that question, number 10 on the last homework. Because I tried to simplify the question by not including the constants, forgetting that there was a minus sign, which you cannot forget, so that was stupid. Now, of course, this comes from turning the double derivatives in x and y, not z, x and y into cylindrical coordinates. And you did that mess, and this is what you got. You know that, of course, you're going to use a separable solution. All of these things are always separable, by the way, so you can just pretty much take that to the bank. So you may think like, well, why don't I just forget about it? You can't forget about it because the way these things work, and you start to see it in this problem, that's why I really probably should have brought this up sooner, is that as you do the separations, the energy part to the Schrodinger equation funnels into one of them and not the other. And that ends up being like really hideously important because energy is energy. All right, so what you end up with is, oh God, let me start over here. So if you feel like writing this down, I wouldn't necessarily, I'm going to do some shorthand. If you don't feel like writing this down, that's not the end of the world. You've already written this down before. And I'm not going to put this on any tests. I just want you to know where this comes from. I multiplied by r squared, and that's so that I can get rid of this r squared here. So remember, that's the whole separability game, and you saw that on the extra credit question on the last exam. And then I've got the wave functions. Again, they're separated. I'm just doing some shorthand. And this ends up being -2 times the mass times energy times r squared over each r squared. And I've already, the wave functions, right, since these are constant, the wave functions, I just went ahead and canceled them out because they cancel out. Okay, so then what happens here is you assume that this thing is, you haven't seen this before, by the way, you assume that your wave function in the angle wave function is still e to the imb, and we don't know what this is yet. Now, again, this is the part that kind of really pieced me off a bit. I don't think that when you're doing math proofs, you're supposed to ever assume anything, but here we are. So if you do that and you insert that in here, and then of course the wave function survives the double derivative, but then ends up getting divided out over here, you end up with just a -m squared. So you have some constants here, you have a constant there, you do some factoring, what you end up with is this. And the point of this, by the way, is to again show you that what happens is the energy, which is the most important part, gets funneled into one of the miniature Schrodinger equations. So I'm gonna put this a little funkily. I'm gonna put ±m squared, just because I think that looks nicer. Okay, there we go, over h bar squared. And I often put these into, I often put all of the business on one side equal to 0 because this is, we go back in time to 1782 when this was solved. And yeah, so basically, x squared dd y squared, x squared d double derivative of y, x derivative of y. Anyway, you go find the exact same thing solved in 1782. I don't see any angles. The angles were taken care of here. And again, 1782, the person solved, Bernoulli, right? Bernoulli solved this equation already and had the functions and had the eigenvalues, which gives us the energy and whatnot. And the solutions end up being, where have I got this? The solutions depend on M. So as I mentioned last time, when you're in one of these situations, the way that they solve this, they had to plug in values for M. You just have to. So you had to plug in 0, 1, 2. Notice it's squared, so you know M can be minus, but it doesn't matter because it gets squared. Okay, so the person solves this, you know, go 17th century people. And these are called Bessel functions. I think that's capitalizing someone's name. And I'm on the wrong board, aren't I? Yep, I'm on the board I can't move, sorry about that. So the solutions are, and that's okay because I'm supposed to be using first capital. So I see that in professional writing. I always have to, like I review a lot of foreign authors' contributions to like Journal of the American Chemical Society, and they often, that's like one of the mistakes, not capitalizing someone's name. So anyway, okay, so they're Bessel functions. Unfortunately, Bessel functions, they're non-analytic. What does that mean?
You have to iterate to get a... Yeah,
it's not straightforward. It's not a sine, right? It's not just a sine over R. It's not like that. It's sucky. It's actually like the integral of cosine minus I sine from 0 to pi or something like that. So it's like in the form of an equation. So anyway, they look like this. There's actually a couple of different solutions, and they're M-dependent. So here's what one of them looks like. And this would be for the M equals 0. That's kind of like the S state. Then we've got one with angular momentum, and that looks like this. So that's the M equals 1. And the energies, by the way, now remember that this is still a particle in a trap. So these are the zeros. So just like particle in a box, where the wave function crosses 0 is the boundary condition that gives you energy. And there's a little formula for that, but anyway, I just want to remind you that, and don't write this down, but this is basically equivalent to particle in a box. Let's center it at 0. Where the wave function is 0 changes the energy. So this has a different energy and a higher energy than this wave function, right? You see that because where it crosses 0, right? This crosses 0 closer to the origin. That means it has a higher energy. And this guy, I didn't normalize these correctly. And this guy has a 0 crossing that at much larger lengths, and that makes it have lower energy. Right? It's more of a localized. So these zeros tell you where the energies are. And again, if you're really interested in Bessel functions, I actually linked it onto the answer key. Okay, so anyway, when you set R equals to a nanometer, then you're actually doing this. So this is actually a subset of this. But because of these Bessel functions, traditionally this class doesn't cover this stuff. So I'm kind of out of line a little bit to cover 2D infinite box problem because we just can't write down easy answers for this. And most people just tend not to teach this. But I kind of messed up by basically I put this in your homework. So I kind of feel the need to oblige to show you what this really is. And again, set the radius to a constant in your back in this world. Last bit, since I've gone this far, I might as well show you the particle in a 3D sphere because I'm on a roll. I think that's an obvious next question. So 3D particle in sphere. Well, I don't need to say 3D particle in a sphere. That's like particle in a circle, particle in an infinite circle, and this would be a particle in an infinite sphere. So the particle's not attached to a string. It can move around inside of the sphere, but it can't cross over to a certain radius because it had infinite energy. So it's sensible, right? Okay, and as you can imagine, of course the wave function is separable. I'm just using shorthand because it's going to suck to not. You know, this is a nightmare. If you don't have a whole sheet of paper, then you need one, or maybe just absorb. I think it's fine if you just want to absorb right now. I'm not going to, you don't have to memorize this. I remember before my PhD exam, I had this memorized. In fact, I actually kind of think I have it memorized right now just because I've been staring at it for a couple of hours. Notice I don't have an I. There's no moment of inertia because you don't have an I until you have to fix the radius to have that moment of inertia, that I show up, and I haven't done that. Okay. Now again, where this problem gets really funky is that I've got an R squared, and then I've got the angle bits showing up. And this is, it's not that we can't separate it, it just makes it harder. And that sucks. Yeah, right here, I've got an R theta, but that's a theta, right? That's a theta. I've got all the angles showing up at once. So this is the guy that's a real pain. Again, it's all just a matter of separating. And of course, the point of all this is to talk about how you end up with a miniature Schrodinger equation, and of course the R Schrodinger equation, the radial Schrodinger equation, ends up being the ultimate solution. Okay, then you end up with the wave functions. And then of course this is equal to the energy. I told you this was a nightmare. Here, I'll write. Now, let me just write this like that, right? I have the wave functions on left and right, so this is just equal to the energy. Okay, so, oh God, now I have to somehow follow my own notes. Now, I mentioned this a while ago, but this guy gets a name because it's such a bear in its own right. It gets its own name. Gendrian. No idea what the Chinese word is. I better figure that out before class. Okay, so if I fix R, then we're back to what we were doing in class before the test. So now now 20 minutes in, I'm now reviewing what we did in class. And what that allows me to do is, so I'm going to do R fixed and go back to what we were doing in class, and I'll actually unfix R and show you what the particle in a sphere is like with an R in it. Let's see, what do we have? So I'm going to ignore the DRs. I'm going to multiply by R squared. And again, since R is fixed, it's no longer an operator. And you end up with, oh, I also multiply by sine squared. I'm doing two sets of algebra between here and here. So you may have a little trouble following it. But again, we were reviewing, I actually did show you this before. Okay, so there's the wave function. There's no R wave function for all the reasons that there's not. Okay, so what happens is I've got, wait a minute, where's my, yeah, I still have this in separated form. Sorry, I got a little confused there. So again, the point is I've multiplied by R, I've got rid of these, I multiplied by R squared. I actually multiplied by sine squared as well. So that's why I've rearranged the terms a little bit. Sorry, that's why I got confused. This is now here, and here's this wave function. Okay. Multiplied by sine squared. That's why that's there. Why that's there. Derivative is there. I should have written these on top of each other. That's that one. Okay, so that's all fine. I changed the order. Sorry about that. It actually confused me. Now what I can do is, I can't forget the fact that I I can't forget my h bar squared, my moment of inertia. There's the sine theta squared again. Okay, now the reason I wrote it this way is that, again, again, you assume that you've got the phi bar. You again assume that the angular z deal is still im phi. And so this ends up just being minus m squared, right? And then what that leaves you is still a mess, a 17th century mess solved in 1782 by Bernoulli, who called it also a Bessel. This is also a Bessel function here. Let me keep writing that down. I just wanted to take a little bit of a break so you can get the board. So we can, yeah, okay, so I can keep working down. Remember I told you at the very beginning, last January, that I'd be writing equations across the board again and again and again and again? That's today. And it gets a little bit worse. What I'm doing now, it gets worse for hydrogen atom. It's a little bit longer. But we'll be done with that in 2 weeks. So anyway.
Question. If we fix r and then multiply through by r squared, shouldn't there still be, even if you take one of those r's and turn it into I with the mass, we should still have an r.
Well, the r is right there. It's in the I.
Right, but there's two of them.
It's r squared.
There is r squared mass.
There is I and r squared.
No, 2 times mass times r squared is I.
Ah.
Right.
So it's not 2 mr. It's not 2 mass.
No, mass times r squared is I. Right. So yeah, it's right up there. So the r's have disappeared here because they literally just got canceled out. All of those were multiplied by 1 over r squared, and r squared is hiding right up there. When I undo, when we are not doing 3D rigid rotor, and I'm going to do that before moving on, when the r shows back up. So right, I know this is kind of mind-bending and not much I can do about that. Okay, so now I'm going to do a couple more steps of algebra. Once I decide that that guy is minus m squared, I've basically separated the thing into miniature Schrodinger equations, and then I kind of start. So when you separate, you apply a wave function and then you divide. Do your separations and then you undo it. So I'm gonna do some algebra, and I'm also gonna undo the separation bit, and I'm undoing it by multiplying by the psi, the wave function of theta. So that might be obvious right now because it's no longer, see, it's not there. Like, where did it go? It's gone because I'm multiplying by it. And the reason I'm doing that is because, and I'm gonna still put this in the same way I did that before, plus minus m squared. And again, I'm doing that because all of these deals are constant. And so I like trying to show this as like plus a constant, where one of the constants happens to be negative. I've got psi. Okay, so there you go. So again, what I did was I made the phi deals minus m squared, and then I multiplied by sine of theta. And again, the reason I did that is this now looks like a regular math equation, right? In math class, you would say, oh yeah, right, that's a differential equation. And you would also recognize it as spherical harmonics. 1782, Bernoulli solves this, spherical harmonics. And again, I'm covering what we did last time. So there are functions that are the answer. You have to plug in a value of m. You have to do that because that gives you the thing to solve. When you plug in a value of m, the only solution has an L of 0. So again, Bernoulli puts nothing in there and finds a solution. Awesome. And the solution, let me write this down, the solution is actually just a constant. And by the way, this ends up being 0 equals 0, right? So I've got a bunch of derivatives times working on a constant equal to 0. See how that's going to work out? a bunch of derivatives working on a constant zero. And that's a zero. So there we go. Let's see. Now, it turns out that if L is 1, there was 3 potential answers. It turns out that there's actually another m equals 0 pops up, and then you get some other. You actually get 3 if L is 1. Question?
So you say the moment of inertia is 1/2 mr squared, but isn't that only the solution for a ring?
Yeah, we're doing a ring.
I thought it was a 3D particle.
Oh, I'm doing that next.
Oh.
Yeah. Yeah, I'm doing that next. So yeah, right up there, fixed R. It's 3D ring. 3D ring. And I'll unfix it next.
Okay.
This is like the easier subset. So yeah, I know I'm not really going the best order here. I really didn't go the best order from the very beginning. So again, do 2 or 3 hours of math to solve this differential equation. I have a textbook that shows how to do it. And then the m value is 1, so I've got I m phi, where the m is plus or minus 1, so you can see that behavior right there. And then if I did L equals 2, I would have m of 0 plus or minus 1 plus or minus 2. And I'll spare you, but it's a bunch of sines and cosines. I wrote them down last time. You have them in your notes. You can look them up. Okay, so the person solves the wave functions, and then you can also figure out what energy is. And that ends up, of course, being a function of the quantum number, because it has to, for all the reasons I talked about before. Always h bar squared equals something over 2y. Okay, awesome. You also see that there's degeneracies. So let's write those down. You can see them here. You can see degeneracies in here. Because the energy only depends on L. If L is 0, there's only one wave function, so there's only one energy, and that's a degeneracy of 1. So if L equals 0, the degeneracy is 1. There's only one answer. If L equals 1, I can see that there's 3 wave functions, and they would all have the same energy. And so because m can either be 0, minus 1, or 1, the degeneracy is 3. And if L is 2, I've got 5 m's that don't affect the energy, so therefore the degeneracy is 5. And if you get confused by that, I'll probably put that on the test some snarky way. It's easy. What do you call an L equals 0? Come up with another word for it. You had it last time. What kind of state?
Ground state.
It is a ground state, but think of another hydrogen-like word.
S orbital.
S orbital. What is this? Yeah, how many are there? 3, and they're degenerate. D is a D. There's 5 of them, right? So you know that. So if you get confused if I ask about degeneracies and whatnot, you actually already know the answer. Okay, last, let me do it. R is not fixed. And again, now I'm kind of like, this is like professionally incorrect of me. We totally don't do R, whenever we do these radial, spherical, radial, cylindrical, we always make R fixed. But I realized I kind of screwed up on your homework again. And I showed you what happens when R is not fixed. Okay, if R is not fixed, oh God. Okay, if R is not fixed, then I just can't spend the half an hour writing this all over again. Let me tell you what happens. It's just like what I just did up there. When I said the angle, the phi part gives me minus m squared. I said phi is the same answer. It's still Im phi. That's the wave function. So the angle bit for the phi bit gives me minus m squared, and that gives me the theta, which gives me the energy. Okay, when I unpin R, what happens is, let me just write it down, and I think you'll get it. All right, for one, I've still got the R's have shown back up again, so here's dVr. They're operating on the radial wave function, which is what we're still trying to solve. There's a slight difference in cylindrical coordinates. Normally this used to be r and now it's 2r. That's what happens when you go from spherical. This is spherical. From cylindrical. Cylindrical, that's just an r. This is 2r. That's the slight difference. Now again, what I want to point out is that here's the angle parts. But I'm assuming that I know them from all this up here. So I'm just going to plug in plus a constant. The constant is minus L times L plus 1. Yeah. And now let's do the energy part. There's the constant. There's my 2 times my mass. There's the energy over h bar squared. So there's our usual kinetic energy stuff. Okay, and then here's r squared. Because you're asking about it. There it is. So when it's not fixed, yeah, you should be able to see it. So again, let's just break it down. 3-dimensional DDRs. Here they are. They're not. They're now. Hello. Here they are because r is not fixed. Here's the angle part. The angle part ends up just being its eigenvalue, yeah. And so you notice I got mass times r squared. So I've got I. Here's my I, except you can't actually do that because r is not fixed. You can't have an I if r is not fixed. So when I wrote above 2IE over h bar squared, this is actually the same, but I'm saying it's not the same because r is not necessarily fixed. And yeah, there you go. So Bernoulli sees this equation back in 1782, knows what the answer is, which are not Bessel functions, but spherical Bessel functions. Now these actually do have forms that you can follow. These you can actually work with, unlike the regular Bessel functions, which are very difficult. You really want to use those on a computer. They look the same. They look almost the same. You'd have to plot the spherical Bessel versus the Bessel functions to see the differences. This is L equals 0. The differences between this one, particle in a sphere and particle in a circle, are incredibly trivial. It's hard to tell. The energy ends up being the 0 times h bar squared over 2 times the mass times the radius. Remember that this is trapped in a particle in a sphere, so there's a radius associated with the sphere. That gives you the energy. And yeah, that's really all I wanted to say about this. Again, just the whole point of this is to always see how energy funnels into sub-Schrodinger equations. Once we do all this multi-dimensional stuff, it's definitely a pain when we're doing it in spherical coordinates. That's the big picture. And I've shown you every type of example problem between the highly unrealistic particle in a sphere, a particle in a ring, particle in a circle with its Bessel functions, and then of course if we're doing particle in a circle, we might as well do particle in a sphere, and you just saw that. And then what we're going to do next is particle in a, particle with a proton, because the reason that this has quantized energy levels, by the way, is because there's a radius beyond which the particle can't escape, right? It's in an infinite potential. Hydrogen atom captures the electron how? Right? There's no wall around a hydrogen atom. Huh? Well, how does a hydrogen atom keep the electron from flying off? Now, the particle in an infinite sphere does it with an infinite potential that exists at a radius and beyond. How does a hydrogen atom do it?
With a proton.
Right, with a proton. Right, a potential that's -1 over r. So it's not a hard wall. It's like an electrostatic pole. It's on a elastic leash. Right, it's like a cat on an elastic leash. And that actually is enough to get quantization and all that jazz. Questions? What's 0? What's that? Zeros are here. So just like in a
root.
Yeah, 0 or root, right? Anyway, just like, remember, this is very analogous to our particle in a box. if you think about the edge of the box being where it can't go further, that actually determines the energy. And you're seeing the same behavior here. It's just a little bit more complicated. And I actually put a link on the example problem I have on the website to show you a little bit about that. Okay, anyway. So I hope that kind of clarifies this. I don't know, again, I really shouldn't have gone into such great detail about this, but I kind of thought maybe it would in some ways clarify how all these, how all this separation and how these sub-Schrodinger equations and how they work. How, you know, maybe if you saw a whole bunch of examples, maybe that would kind of help it stick. And now we're going to go beyond this, and I want to point out that this next lecture, we're going to be doing hydrogen atom. There's one last thing. So hydrogen atom still assumes that the spherical harmonics, that's L equals 0, the wave function's constant, L equals 1, the wave function's sine, cosine. Hydrogen atom assumes that those are the radial, the angular parts, the angular parts. The energy is solved by the radial part. Now the radial is not the same as this, obviously, because instead of, this guy has its energy because outside of a certain radius there's an infinite potential. Hydrogen atom does the same thing, but with an electrostatic pole, the energies are not the same. The wave functions are not the same, but they're awfully similar. Okay, last thing I wanted to go over, so let's go back to 3D rigid rotor. And I want to point out that whether I'm doing particle in a 3D sphere, 3D rigid rotor, hydrogen atom, all the wave functions are the same, the angle parts. The angle wave functions are the spherical harmonics, what I drew a little while ago with the theta and phi of it. The wave functions for angles are always the same. That's the take-home lesson. Even if we did 2D, 2D rigid rotor, the wave function is still e to the I m phi. When we went 3D, then we get sine theta, cosine theta, yada, yada, yada. It's all the same. So anyway, but now when it comes to, and then we're going to see that in hydrogen atom. Now I wanted to go over a little bit more about nuances of the energy. So the energy, and again, we're doing a 3D rigid rotor. So there's no radial part with the energy. So I'm kind of working backward. So we get this deal. This is the energy. Okay, and L of course is quantized. That's where the quantum mechanics comes from, and that was just because when the person was solving the equation, it just that there was this index of answers naturally pops out of doing the work to find the solution. Now I want to point out that there is, if this is j squared over 2i, where j squared is the angular momentum squared, angular momentum over 2 times the mass is, of course, the energy. That there is an associated operator, which is r cross p. P is still derivatives in x, y, and z. And where this gets a little bit nightmarish is we can do it this way, and what you'll find is that once you do all the bloody vector this and that, cross product this and that, you find that you can describe it this way. Like any vector, the square of the net vector can be broken down into x, y, and z components. That hat's in the wrong spot, anyway. Okay, so again, you know that, or maybe you've forgotten, that's fine. Angular momentum is r cross p for something moving in a circle. And do all the bloody horror show of the calculus cross products, vector, this, that, and you find that you can break it down into this form. And then if you do something akin to what we did on the homework 7, you can find something that's not too surprising. You got an h bar over I, or it gets a little bit complicated, and it's complicated in the same way that problem set 7 was complicated. It takes about most of a class period to show you how to break down the angular momentum and its x, y, and z components. I always see an h bar over I. Remember whenever we have momentum, there's always an h bar over I. It pops open every time. Always is there. There's a little bit of a pattern to y ddx minus z ddy. There's a little bit of a pattern, but whatever. And again, don't even try to memorize all this. Don't, because I'm not gonna, sometimes I put these on tests, but not, your class I don't feel like it. I haven't spent enough time emphasizing these. Z ddx, and again, there is actually a pattern to this, but whatever. Okay, so these are the operators, so I can take those spherical harmonics, and I can operate on them, and then I can get the momentum, and then I can square it and divide it by 2i, get the energy. It all makes sense, right? So I'm just taking the final result, and I'm kind of breaking it down. The final result, again, is momentum squared. So I'm breaking down momentum into its pieces, its component x, y, and z pieces. It gets a little complicated because, like a vector, the magnitude of the vector is r squared is x squared plus y squared plus z squared. It's just I've got a j instead of an r, right? It's just that easy. Except that then I've got this horrible. So it's awful. Okay, now the reason I'm going over this, and again, I don't expect you to know this. Okay, once people, it's like okay, well, I have the energy, right? I have the energy, and I've got the wave function. So what? It turns out when they bothered to do all this, break down the pieces, they discovered something. And it's really important. This is how NMR works, by the way. I'm going to show you how they figured out how to do NMR. Because they bothered to break down the, it's like, okay, you're here. Why go further? You're done. This is the answer. Here's what you discover. You discover that you run into an uncertainty principle. You run into an uncertainty principle with Z. You find that there's an uncertainty relationship between Z and Y, and you find that there's an uncertainty relationship with Z and X. I won't be able to go further with this. I'll have to save this for next time. Then we'll do hydrogen atoms. Okay, so here's the thing. Again, I hope that breaking down a vector into its x, y, and z components is not particularly difficult. This is still r squared is x squared plus y squared plus z squared. The net divided by 2i is the energy. I hope that's all clear. Now, you understand how I'm going to run into jazz like this because of momentum, because momentum is a derivative. And then what I get from that is I get uncertainty principles. But what it means is, this is the basis by which NMR works. I'll just give you a little bit of a hint. If I have no projection, if I have no z component, so remember if I'm doing this, where's my jz? Point it up. All right, now that's in the z direction. So if I'm doing this, do I have a z projection? What will I do? It's just 0. Right, so no, or it's 0. Okay, now here's the thing. So you know the z component, right? It's 0. So what's the y component and x component? Can you know? All right, if you have infinite knowledge of the z component, and you do because it's 0, and 0 is a definitive number, then you don't know the x or y component. Now, what does that mean? It means this. It means when something is rotating, you know that it's doing this motion, you don't know where it faces. Seriously, you don't. So when H2 is rotating, if it's rotating just like I'm doing like right now, seriously, if it's doing this, and I'm going to just model that this way, then you don't know, you don't have this information. That is what allowed these 2 or 3 Nobel Prize winners to develop NMR. That fact allowed them to develop NMR. And I'll cover that next time because I've gone over. Anyway, yeah, all right, I'll see you all next day.